and I confirm that I would like to dedicate the first couple of hours to up to more or less to teaching, lecturing, and then 2 hours exercises on the PC. It's not a real exercise today, it's an introduction to the software that I kindly asked you to install on the PC. And if you didn't install it yet, don't worry, we can do it together later. So just let me show you that I updated, this is the page in IOL dedicated to the course. I updated the links, so you can find the links now to the new lectures. And if you go on my website as well, there are a couple of links more. We concluded last week talking about the mechanics of sea waves. Before I start, just one thing, I need today to keep the phone on, because I have some urgent commitments, so I hope I don't get any call. If I get some calls, maybe I take a couple of minutes to reply. Okay, so we talked, as you may remember, about mechanics of sea waves, and it was just a brief overview, because as I mentioned to you, I assume that Professor Archetti already introduced the mechanics of sea waves to you. And I mentioned to you what are the questions that I may ask, like what is, how to derive the Laplace equation, what are the boundary conditions. I don't need a description in mathematical terms because it's a bit complicated and it's to be learned by memory, which is not my purpose yet. But I may ask you what type of boundary condition we impose, and it's just fine if you describe by words. And I can also ask you what is a plane wave. You know that as a premise I said we focus on plane waves. And I may ask you what is a wind wave, what is a sea wave, how it's originated, is it a transfer of mass or a transfer of energy? These are typical questions that may be asked. And I also will prepare a self-assessment test for you where we put some of these questions. Okay, and that's it for wave mechanics. Let's now talk about wave transformation. I know that you already had some introduction to these effects, so my overview will be very brief, but I think it's important to summarize what are the kind of transformations we are interested in. I know that there is one student, maybe two, among you that didn't attend the lectures by Professor Archetti. In this case, it's you, maybe, yeah. In this case, I think what I suggest to do is to look at the lecture on sea wave mechanics. It should be self-understandable, and but if you have some problems, let's talk about it. Okay, that's fine. Any other student, you too. Okay, so the same for you. Just have a look by yourself, and I think should be clear. You don't need to understand everything, and because when it becomes very mathematic, just you can leave it. I told you what are the type of questions that I may ask. Okay. And the same thing for wave transformation. This is more descriptive. It's not really quantitative, and I just want to summarize what I'm interested in. I am interested in recalling the concept of wave refraction, diffraction, and shoring. I'm not interested in the concept of wave reflection because it doesn't apply to our coastal engineering structures. And I guess that you know what is also reflection, but again, I'm not really interested. I'm not asking anything about reflection. I may ask you, what is wave refraction, for instance? So what is wave refraction? It occurs, when we talk about waves, refraction occurs when a wave passes through from a medium to another type of medium, like a wave, a light wave that is passing from air to water. In our case, we don't change the medium, but we know that when waves approach the beach, the coastline in general, there is a decrease of the sea depth. And this decrease of sea depth, basically it acts like a change of medium. It's a change of the properties of the medium. Why is that? Because with decreasing sea depth, waves start to interact with the sea bottom, and in particular we have friction. So the fact that waves, while traveling in the same medium, which is salt water, at a certain point are subjected to friction, it is like a change of medium. And what happens is that the interaction with the sea bottom with a plane wave doesn't happen at the same time along the transversal direction. Keep in mind we have two directions, the vertical direction, when we talk about a wave, the vertical direction. We have the direction the wave is traveling along, I call it the longitudinal direction, and we have the direction that is perpendicular to the longitudinal direction, I call it the transversal direction. So basically, if you look from the top to a wave, and this is the wave crest, the wave is traveling along this direction, it's a plane wave. Keep in mind, the fact is that it's a plane wave, it means that after 1 second, if I draw the wave crest, it's here. So, the wave crest, it's displaced in a plane that is parallel to the plane where the previous wave crest was. So propagation occurs along a sequence of, an infinite sequence of parallel planes. It means that the wave direction doesn't change. Okay, so this is the wave direction, and I call it also longitudinal. And then we have the direction that is perpendicular to the longitudinal. It's the direction along which the wave crest is displaced. This is transversal. Transversal. Okay, so at a certain point, the wave starts interacting with the sea bottom, as I said. And this interaction, if I look at the transversal direction, doesn't occur at the same time. We have interaction that starts, first of all, here, and later on there. So what is the effect? The effect is that the part of the wave that starts interacting with the sea bottom slows down its speed. The other part of the wave keeps the speed, and therefore the wave bends. So it's no more a plane wave in a strict sense. Okay? But bends. So basically what happens, you can look at this picture here. What happens is that the wave, the transversal direction, tends to align with the coastline. So if I have a coastline here, coastline, and the wave comes from here, then subsequently the wave starts getting this shape. So the wave tends to approach the coastline perpendicularly. This is the wave direction, the wave direction changes. This is refraction. Again, it involves an interaction with the sea bottom. caused by interaction with the sea bottom. So this is the distinguishing feature of refraction. Okay. The result is a change of wave direction. The result is also change of wavelength. It's a change of speed and wavelength. Okay. Now let's talk about diffraction. What is diffraction? Diffraction is originated by the interaction of the wave with an obstacle, like a breakwater. Do you all know what a breakwater is? Just, okay? Everybody knows what is a breakwater, because Professor Archetti talked about it. I see your faces a bit.
I didn't attend Professor Archetti.
Okay, you too, so didn't attend. So you don't know what is a breakwater, okay? Okay, so let me show you a picture of a breakwater. Let me take the correct picture. This is a groin, this is a breakwater, but it's not very representative. Let me look for another picture. Ideally, I would like to see a picture from the top. Strange, okay. Okay, sorry, this is a video, it wasn't interesting. But this is a breakwater. It's a structure that emerges from the sea and it's parallel to the beach. And usually it's made by boulders. And we have to distinguish between the breakwater is parallel to the beach. And all the other structures that I see here, they are groins actually. Groins are perpendicular to the coastline. So let me go on the top, because I saw, okay. So if we look at this picture, what we find here, let me see whether I can, okay, now it's clear. On the left, you see a groin. It's a groin with a carved shape. Usually it's perpendicular to the beach. In this case, it is carved. It's called a T groin. It's not really a T shape, this one, but it's like a L shape. And it's basically a shaped groin. And on the other, on the right, you see a breakwater. It's connected to the coast, but at the end of the story, it is displaced. When it is displaced parallel to the coastline, it is called breakwater. When it is orthogonal, it's a groin, and they can be mixed. Actually, what we see here is a composition. It's a groin that is connected to a breakwater for both the shapes. And the purpose of these structures is to block the waves, so to block the waves or to attenuate them. And the reason is that why they want to block the waves, because they want to prevent erosion. We will talk about it, the erosion of the beach. Okay, so when the waves meet these structures, they, of course, they are impacted by the structure, there is an interaction. And the interaction is not due to the fact that they interact with the sea bottom. It's an interaction with the structure. So, in this case, we talk about diffraction. What happens in this case? It happens that what happens is that, let's suppose that you have a wave that is traveling. It's traveling along this direction, and then the wave meets a structure like this one, like a breakwater. This is the breakwater. And here we have the coastline, which is parallel to the breakwater. This is the coastline. Okay, what happens then? What happens is that, of course, the part of the wave that goes against the breakwater is blocked. But then the breakwater finishes. At the end of the breakwater, the wave continues its traveling. So what you may expect is, what happens then? You may expect that here the wave approaches the breakwater, and then you have a continuation of the wave here with the same direction. This is what you may expect. It's not like that. What happens is that this wave, while traveling, bends behind the structure, and therefore there is a propagation of the wave in the lee zone. The lee zone is the zone that is protected behind a structure. It's a quiet zone. There are no waves because they were blocked by the breakwater. This is called the lee zone. So the waves bend behind the structure and propagate into the lee zone. This is diffraction. This is diffraction. Again, what is the difference between refraction and diffraction? If you are asked this question, you should simply reply, refraction of sea waves is caused by interaction with the sea bottom, a differential interaction along the transversal direction. Diffraction is caused by an interaction between the wave and an emerging structure or island. Of course, keep in mind that the two effects may combine, because if the wave, if the structure, it's not a structure but it's an island, then you have the effect of diffraction, wave that bend behind the island, but also the effect of refraction, because the sea bottom, of course, in the proximity of the island is gaining elevation, and therefore the water depth is decreasing. So very often you have an interaction of the two phenomena, but if you want to make a difference, refraction is caused, again, by interaction with the sea bottom. Diffraction is caused by interaction between waves and emerging bodies, structure, islands, etc. So you may wonder, what causes this? Because it's clear what causes refraction. If you have a part of the wave that slows down and the other part of the wave that continues at the same velocity, of course you have the fact that the wave is changing its direction. This is easy to understand. In this case, what is causing this change of direction? What is causing this propagation of the wave into the lee zone? This is more difficult to understand. And the reason is that actually each fluid particle that is moving up and down in a wave, each fluid particle is originating, due to its movement, a secondary spherical wave. So it means that these particles that go up and down along the, let's say, the main wave, in this up and down movement, they originate as very smaller secondary spherical wave. Spherical means that it propagates in the longitudinal direction and in the transversal direction. So, when the wave is undisturbed, basically you don't see these secondary spherical waves because they occur along the whole wave crest. But when the wave, part of the wave is blocked and the other part of the wave here gets in touch with the calm zone, the lee zone, then there is this spherical wave that you notice. And it causes a movement of the particles into the lee zone. It causes a wave propagation into the lee zone. So this is why this secondary wave is the physical explanation why you see this propagation of energy into the lee zone. Again, you can see it because this zone is quiet, is calm. So, if you look at my website, there is a link to a video that I suggest you to have a look at. Here. Which is nice, it's in English and explains what is diffraction in a way that is easy to understand, I think. And you see here, let me because we are not looking at the whole video, it's 4 minutes. But if you move forward, you see here examples of wave diffraction. At the end of the story, what matters to us is that these structures and the coastline, when waves approach structures and the coastline, there is a change in wave direction. Why we are interested in this change of wave direction? Because waves, as we will see, have the capability to move sediments when they get close to the beach. And we have to understand the direction of waves because the direction of waves dictates the direction of moving sediments. Okay, let's now talk about shoaling. This is another transformation that you already know about, some of you at least. And this is a nice picture showing what shoaling is. When there is the interaction of the wave with the sea bottom, it happens that the wave decreases the wavelength and increases the amplitude. It's just a matter of conservation of energy. If you impose the conservation of energy in a domain that becomes restricted, because the water depth is decreasing, if you impose the conservation of energy, you get a decrease of wavelength and an increase of wave amplitude. And what happens, you can see up there. Remember, the waves do not originate significant mass movement of water. It's just a transfer of energy. And this is something that you learned already if you attended with Professor Archetti. There is indeed a small mass movement because basically it's not just an up and down of fluid particles. It's an up and down with some circularity, but the mass movement is very small. It is basically a wave, it's a transfer of energy which provokes an up and down. So there is no transfer of mass. But the situation changes when you get close to the coastline. Why the situation changes when you get close to the coastline? Because of shoaling. Because with shoaling, waves increase their amplitude, and at a certain time they become so steep and so high that they break. And they break in a position that is more or less constant during the season. It varies with seasonality, but during the same season we have more or less the same characteristic of waves, same amplitude, same frequency, and same position where they break. And when they break, what does it happen? Suddenly they change their behavior because a movement of mass is originated. There is a lot of turbulence. When they break, there is a lot of turbulence. And as the surfers know, there is a movement of mass that is triggered, that is started. So we see water after breaking that travels very quickly towards the coastline. And the water runs up the beach and then it comes back. And there is an up and down that it's originated. This up and down is clearly a movement of mass. So there is a point, which is called the breaker line, where the movement of energy is transformed into a movement of mass of water with a lot of turbulence. And this zone from the breaker line to the coastline is called the surf zone, for obvious reasons, because this is the zone where the surfers have fun. Because the movement of mass means that they can surf. Otherwise, they would just go up and down, which is not really fun. And it's called the surf zone. Okay, here there is more mention to bottom friction. Now, I think at this stage, what I would like to do is to introduce to you the structures that we can use to prevent beach erosion. But before doing that, I would like to anticipate some terminology. I already started breaker line, surf zone, shoaling. Let me now to go into more details on the terminology for beaches, terms for beaches. Now, let me then go back here. And in order to introduce terms, I jump to the last lecture that is linked here, because I need a figure. Here is the figure that I need. Okay, I think this is what we need now. Okay, so let's look at this figure. We have the offshore zone. We know what is that, and usually if you look at the offshore zone, the bottom of the ocean is not sandy, it's just rocky in most of the cases. Keep in mind that if in some seas, and also in some oceans, but it's more a feature of the sea, the offshore zone can be reached very far from the coastline. If you have the bottom slope of the ocean that is decreasing very gently, it's a mild slope, you may have sand for hundreds of meters. But when you get very far from the coastline, usually you don't get any more sand on the bottom of the ocean. Because you get, sand is transported by the rivers, is transported by the land, and it's transported in the offshore direction by the waves and the currents. But at a certain point, the waves do not imply any movement of mass. As you get in deep ocean, they don't imply any movement of mass. And therefore, the sand is not transported very far away from the coastline. So typically, the sea bottom in the offshore zone is not sandy. And then when you get close to the coastline, of course, the depth of the sea decreases, and therefore you start to observe an interaction with the sea bottom. An interaction with the sea bottom means friction. Friction means transportation of sediments. So when you have a depth that is decreasing, then you start seeing some sand because it's transported by friction. And it comes from the land again. And also interaction with the sea bottom means shoaling, and at a certain point you reach the breaker line. So when you reach the breaker line, typically it is reached when there is a decrease of the depth of water. So you see the breaker line, it's not put in evidence there, but it is placed here. You see that here there is a wave that is breaking, and they break when the sea bottom becomes close to sea surface. And then here you have the start of the surf zone. Keep in mind this terminology. When you start having an interaction with the sea bottom and up to the breaker line, we call this zone the lower shore phase. After the breaker line, the surf zone is also called the upper shore phase. The upper shore phase extends from the breaker line up to the upper limit reached by water. So this is basically the high water mark. Its position depends on the season. So this is the upper shore phase. The surf zone is not extended to the upper water mark because it's also called this upper water mark limit of run-up. What is the run-up? Is the up and down of water. The surf zone is not extended to the run-up zone because you don't surf in the run-up zone. You surf where you have enough water. So there is a small difference between the surf zone and the upper shore phase. Okay? An important thing, at the breaker line, you see a bar. What is a bar? It's an accumulation of sand displaced along the transversal direction. Why there is accumulation of sediments at the breaker line? Because, as I said, at the breaker line, you have a movement of mass that is originated. And this movement of mass implies a movement of sediment. So, basically, if I have here the breaker line, and here we have the wave that breaks. Then we have a high turbulence in this zone. Turbulence. Mass movement. Okay, and then here we have the limit of run-up. This is how it's called, the limit of run-up. Good. So what happens here? It happens that if I depict in black the sediments, I have a movement of sediments that originates here in this way. Which is associated with the movement of water. So here, associated to this turbulence and this movement of mass, I have a movement of sediments. And then these sediments, when they come back, they collide against the wave that is coming from the offshore zone. So here, what I have is a deposition of sediments. And this deposition of sediments is the bar. The bar identifies the position of the breaker line. And it is something that can be easily perceived. If you walk during the summer, if you walk into the city, you can perceive that you get your water maybe up to the knees, and at certain points, if you keep walking, you perceive that the sea bottom is coming up, and then you have water maybe to the ankles, not more to the knees. And this is the position of the bar. The position of the bar is clearly seasonal. Clearly seasonal. This is why, if you look at this picture, you see that the time scale of evolution that you can see in the bottom of the picture, in the proximity of the upper shore phase, is months, because the upper shore phase is shaped with the seasonal process. This is a question that I may ask you, like, tell me what is the time scale of evolution. We will discuss more about this. Of the beach. So the bar, the time scale of the evolution of the bar, what is? It's a seasonal time scale, monthly time scale. If I look at the offshore zone, the time scale of evolution is thousands of years. It's related to tectonic movements. Where you have sediments, you understand that sediments are easier to move than the rocky platform. The rocky platform moves according to tectonic processes. The sediments move according to seasonal processes. But again, what's important is to identify the bar. Okay? Then, if we look up the limit of the run-up, we see that at the limit of the run-up, which is seasonal again, there is the position of sediments. Because sometimes we have gravel that reaches the limit of the run-up, which doesn't go back. And therefore there is another accumulation of sediments. So here we have this circulation of sediments, and the limit of this circulation area, you have the position. And the deposition that you have here is called, here the scale is amplified, berm is not so steep. Here I exaggerated. But basically you can see this elevation of the beach, and if you look behind the berm towards the land, you see that very often you have a kind of depression which is filled by water, calm water, salty water. You have some water there because indeed after the berm you have a depression of the level of the sand. This accumulation of water, if present, is called runnel. These are all features that can be easily observed in our beaches here, because they are very sandy, as you know. On the Adriatic Sea you have a lot of sandy beaches.